So much drama in the LBC. It's kind of hard being Snoop D-O double G, but I somehow, some way keep coming up with funky ass shit like every single day.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
In this problem, we have a wheel that is pivoted at the center and it rotates without a friction. There will also be a constant tangential force, F, that is applied to the rim of the wheel. So this could be, for example, a rope that is unwinding as it's being pulled and hence accelerating the wheel. And we know that starting from the rest, the wheel has angular speed of 12 revolutions per second after 2 seconds. How can we evaluate the moment of inertia of the wheel from this information? Let's start by analyzing the torque. So we'll use the simple formulations. There's no need for vectors in this case. So we just make the claim that the axis of rotation is the z-axis. So we can denote the torque as T sub index C. So tau Z. And that is, in this case, when the force is completely tangential. So we have F tan tangential, and then the distance from the line of act to the pivot point. So that's R. And F tan is just Fr. And the magnitude of the force is 80 newtons. The radius of the wheel is 0.12 meters. So we get constant torque of 9.6 Newton meters that is being applied to this wheel. And what can we learn from that? So eventually we want to get our hands to the moment of inertia, and that is of course involved in this relationship which relates the net torque acting on the wheel and its angular acceleration, alpha. So in order to solve the moment of inertia, so that's of course about axis C. So in order to solve moment of inertia, so we need the net torque and angular acceleration. But we can learn something else from this relationship as well. Now that we have constant torque right here, and moment of inertia is a constant, that means that the angular acceleration in this case will also be constant. So we have means of evaluating that based on this information. So after 2 seconds, the angular speed is 12 revolutions. So that is constant angular acceleration, for which we have the relationship omega z is the initial omega z plus constant angular acceleration times elapsed time. And this is 0, so we get for angular acceleration to be simply omega z at some time t divided by the time t itself. So omega z is said to be 12 revolutions per second. So we have 12, and 1 revolution is 2 pi, the whole circle. So 12 revolutions per second like this, divided by 2 seconds. So that gives us 12 pi radians per second. We don't always explicitly write the radians because it's a unitless number, so we can use 1 instead. Okay, so now that we have found that, we can go ahead and put the net torque there. So that's 9.6 Newton meters divided by the angular acceleration that we just got. So 12 pi radians per second. And the magnitude is 0.25. Well, let's see that we get consistent units. So Newton meters. So that's going to be Newton is kgm over s squared times the meter divided by, oh, that's second squared, of course. Second divided by second, like this. So these seconds go away, and we have 0.25 kilograms times meter squared, which indeed are the units of moment of inertia.
With my mind on my money and my money on my mind. Rolling down the street.